Yes, okay everybody, welcome back to the second day of the jointly held DNS-OARC 39th workshop and the 47th Center Technical workshop. My name is Willem Torop. I will be the session chair for the first two sessions today and also the last session today. The timekeeper today is Manu Bretel, sitting over there. The very last slot will be lightning talks, and you can still submit until 12:30 today. And we will review after that time the number of submissions we have and make a selection for the very last session. Questions and answers are posted in the Mattermost workshop channel of the DNS-OARC Mattermost. And you have to prepend hashtag questions, preferably with an S behind questions. And then I will read them out loud after the talk ended. Except for people that are in person in the room here, they can just walk up to the microphone and ask the question there. But I will handle the answering questions. After the second session today, it will be lunch, and there will be a Women at ORC lunch table with 8 seats, and it's a long table in front of the 2 round pillars in the restaurant. They will have a sign on it. There's 8 seats, and you can bring male allies as well. It's not only for women. So I'd like to thank the hosts of today, which is Runnits and SOX, and Center for being a joint program partner, and VeriSign for being the 2022 workshops patron. So you see on my badge there's a word mentor. There are other people here in the room that are a mentor, and that means that if you are a first-time attendee or you're not a first-time attendee, but you will need some help getting to know people, or if you have questions about DNS-OARC, you can walk up to a mentor and he or she will help you with those things. And I think it would be convenient if everybody who is a mentor would raise their hand now, so people can see who they are. Yes. Excellent. So, just before the summer holidays, I'm at NLNet Labs. We had 2 students that did a master program with us, or did a master thesis at NLNet Labs. And they were excellent students. They were Sander Post and Brice Habets. And they are going to give the first talk of today, which is the talk, a quantitative analysis of authoritative DNS servers and their RPKI adoption. So, Sander, Brice, take it away.
Okay, Willem, thank you for introducing us. As said, I am Brice Habets, and Sander Post will come on the stage in a second. We did this master thesis together, so we thought presenting together is fitting. Yes, so a quick overview of what we're going to do. We're going to introduce the topics, give you some background information, talk about some related work that we found. We'll be talking about our methods, our results, the discussion, and of course our conclusions. So as we all know, DNS and BGP form the basis of the internet. However, they weren't designed with security in mind. This means that we have to add security on top. And for DNS, we have DNSSEC. And for BGP, one of the solutions is, of course, RPKI. And this RPKI, it makes use of databases. And within these databases are maintained by the regional internet registries. Within these databases, we have objects called route origin authorizations. And such a route origin authorization contains an IP prefix, autonomous system number, and a maximum prefix length. And on these route origin authorizations with this database, we perform route origin validation. So we set out to answer some questions. Our main question was, what is the state of RPKI adoption on authoritative name servers? And we had some sub-questions to go with that. And we did this because, as far as we know, research into RPKI adoption and ROV adoption on authoritative name servers hasn't been done before. Okay, so route hijacking. What is it? It's when we maliciously or unintendedly reroute traffic away from the intended destination. There's multiple ways to hijack, for which I refer you to the source at the bottom of the page. We just focus on the traditional subprefix attack. This is where we announce a more specific prefix from a different location. And this should have a global impact and thus, impacting the whole network. It does generate a lot of noise, but we don't really care about that as we own the infrastructure that we'll be hijacking. And with noise, I mean it can, if this is done on an unsuspecting target, it can disrupt global connectivity to the target. And many BGP monitoring systems flag the sudden change in origin autonomous system. So the RPKI, like I said, it's a resource system which is used to validate BGP route advertisements. It's a hierarchical public key infrastructure which contain prefixes. The end owner is actually IANA. However, they delegate trust anchor function and resources to the regional internet registries, which of course can be delegated further as seen in the picture. Goes from the regional internet registries to the local internet registries if they, or national internet registries if they're present. Then we have the local internet registries and then of course your ISPs. So within this RPKI, resource certificates are issued, and these, in these, a public key is bound to either an IP address or an autonomous system. And we have these end entity certificates which are used to sign resources, and they cannot sign other certificates. And of course, the owners of a prefix can create such a route origin authorization which identifies which prefix can originate from which AS. So to interact with this RPKI, we have a software which is called the relying party. And it has four basic responsibilities. The first one is caching, fetching and caching the RPKI objects, processing certificates and certificate relocation lists, processing signed objects, and distributing the validated cache. It does this with the RPKI to router protocol within your own autonomous system. And an example of this software is Routinator from NLNet Labs, but there's different ones available. One we thought of is also RPKI client. So then how does that look? Most of us probably know this, but it's just like a DNS. You go from the regional internet registry to national internet registry, local internet registry, and your ISPs. And then within our AS, we have our normal BGP traffic. So some related work. In 2020, Linsen measures the protection of 11 top-level domains, including the .com zone. And in the end, they conclude that 45% of the domains are covered by a route origin authorization. And in this research, they only look into route origin authorization. Where we differ, we also include the route origin validation status. So then we'll get into our setup, how we tested all of this. The most obvious first, we have our valid announcement. And for this, we chose a /23 for IPv4 and a /47 for IPv6. Then we add our invalid announcement, or our hijacker. And in this case, we chose a /24 and a /48. So far we have 2 geographically separated locations, 2 separate ASs, however the separate ASs are optional, and 2 different upstream providers. And with these upstream providers, it's important that our valid upstream provider does route origin validation and the invalid one doesn't do it. Because if the invalid one also does route origin validation, our hijack responses will never arrive at the hijacker. So then we get into data collection. For this, we of course need a querier. It shouldn't really matter where you put it. We just put it in the valid announcement location. This sends DNS requests to authoritative DNS servers without waiting for responses. And in this, we specify the source port, the source address, and the domain name, and we match all of that to make sure that the responses we get are actually from our querier and not some other normal DNS traffic tainting our results. Then we also need 2 collectors, 1 at each site, and this listens on the specified port, and then we log the timestamp, domain name, and IP address for further analysis. So, what does it look like? If everything goes right, then we send our query from the valid AS, and then everyone does route origin validation, and it ends up back at our valid AS. And then, of course, if somewhere along the way route origin validation isn't present, then it ends up at our hijacker. Now, Sander will take the word from here.
Thank you. So yeah, we had to feed our list of IP addresses onto the querier, and luckily we got a huge data set from OpenIntel, which is a joint project for where also NL Labs is involved in. And it included IPv4 and IPv6 addresses, and we also had a lot of domain names. Those domain names were later used to correlate with the results that we had. So in what order did we feed those queries onto the querier? So in the first case, we basically made an ordered list, and we ordered them. And we fed all those IP addresses for 1 hour to the querier, and we did that for 4 days straight. After that, or while that, actually, we thought to ourselves, well, what if we hit some rate limiting? So the second experiment that we did is basically based on a pseudo-randomized list of all those IP addresses. And now I want to go into the results that we have. So this is a general overview of all the results. On the left side, you see IPv4. On the right side, you see IPv6. So if you look closely at the labels with the percentages, they do not add up to 100% because we basically discarded all the responses that we did not get after the queries were made. So in general, we can see that for IPv4, around 43% of the responses arrived at a valid collector, and for IPv6, that was around 37%. And also note that the IPv4 space is around 900% bigger than the IPv6 space. So on to the next slide then. This is basically where we correlated the first results with the actual domains that were served by those authoritatives. And this basically gives us a different overview of all the results that we have. So the first thing that we can see is that, well, there are a lot more IPv4 reachable domains than IPv6 reachable domains. And proportionally, we can also say that there are more IPv6, the IPv6 is basically better protected by route origin validation from our results than IPv4. So my colleague just described two scenarios where a query response would arrive at a valid or an invalid collector. But the thing that we've also seen is that during an experiment and during a day, we can see those responses basically arrive at both a valid and invalid collector. So the amounts are not that huge. However, on the 24th of June, we can see a huge outlier, and until this day, we still do not know what happened on that day. But we've seen a lot of duplicates on both valid and invalid collector. The last result that we have here, this is basically where we correlated our general results of the IP addresses of all those authoritatives, and we tried to correlate them with validated ROA payloads. And in this case, we can see that basically a lot of IPv4 and IPv6 reachable authoritatives are covered by ROA. For IPv6, basically around 78% is covered by a ROA from the total. And for IPv4, that's around 74%. So in this case, IPv6 is doing a bit better. And around 40% of the IPv4 responses arrive at the valid collector. And IPv6, that's around 50%. Yeah, so these were the results. And now I want to continue on to what we've, well, whoops, sorry, what impact that we had. So first of all, well, we showed you a general overview of the current state, but also if we want to, if our data set is comparable to the one that was used by Linsen in 2020, then we can see a steady increase of 66%, around 66, of authoritatives covered by ROAS. However, it raises a question also with those duplicates and responses that did not arrive. So the internet is dynamic, right? So very dynamic. And yeah, how can we show that to you? And we have a discussion about weakest link here, where we want to introduce you a valid and invalid ASs. So in the center in this picture we have a validating AS, then its peers are also and all non-validating ASs. So in this case it is still possible to perform a sub-prefix hijack, even though that the valid AS is dropping invalid routes. And to correlate that to our specific experiments that we had with the authoritatives. So on the bottom or on the top illustration, we have a non-validating upstream provider, but our authoritative name server does reside in a validating AS. The response that we get from the authoritative, in this case, will arrive at an invalid collector because our upstream is non-validating. However, in the bottom path and the bottom illustration, we can see that well, our upstream provider is actually validating, and in this case, our response will arrive at a valid collector. However, what if our AS or what if our authoritative name server does not reside in a validating AS? Well, in this specific case and in this specific scenario, we can still see the response arriving at a valid collector because our upstream provider is actually validating the routes. So, for future work, we discussed that with my colleague, and we came up with two main things. The first thing is how dynamic is the internet really? The idea that we had is just measuring a specific path from A to B or a specific source to a specific destination and how much that path really changes over a specific amount of time. And the second idea that we had is a trace ROV tool, which is, well, comparable to our experiment setup along with just the trace path idea. And in this case, we can just measure what's going on the internet and what ASs validate and what ASs do not validate. So, a conclusion. From our experiments, we measure that on average 45% of the queried authoritative name servers do reside in an autonomous system that is doing route origin validation. And on average 67% of the domains served by those authoritatives also reside in an AS doing ROV. We showed that the internet is a dynamic place, along with, the weakest link problem that we've shown you. And also, we've seen that responses arrive at a valid and invalid collector. We can also see that RPKI is steadily increasing at this point in time. And sub-prefix hijacks are still possible this time. So I want to thank you all for listening, and also special thanks to Willem and Tom Carpe from NL Net Labs for supporting us with this experiment and with this thesis. Thank you.
Thank you, Sander Brice. We have 4 minutes for questions. Jeff.
Houston APNIC. Authoritative name servers can best be described as promiscuous answerers. They'll answer anyone or anything. Why should they care if the IP address they're sending a response to is valid or invalid? They're going to answer everyone. So as far as they're concerned, it doesn't matter. So I'm finding it hard to sort of understand why you set up an experiment to measure the fact that authoritative servers will answer anyone, because the answer is, sure they will. Surely the real question is whether it is possible to me to launch a route hijack to hijack the authoritative name server. And because routing is positional rather than absolute, the real question is, to what extent are paths to authoritative name servers hijackable, which is a much harder thing to ask. And I didn't quite grok from your presentation whether you had done that analysis or not.
Right. Yeah. So should I answer?
Yeah, sure.
Yeah. So those are good questions. In the end, an authoritative might not care about where the response ends up, but thinking about how we all use the internet and we all want to be protected, I guess it would be in their interest to do it anyway, because others might also want to protect them. But yeah, of course, in the end, it shouldn't really matter if the authoritative does it or not, because they're going to answer anyway.
So can I add to that a little bit?
Yeah.
Because I assumed the same in the first instance, but I thought, we're going to do it anyway, just to see if they are validating and then comparing it with whether they are signing or not. But, so initially, Sander and Brice used AWS for the valid announcement. And later on, we also used Vultr. And we used a faraway Vultr node, for us, that is, very close to you, namely in Sydney. And so the invalid was in Amsterdam and the valid in Sydney. And we noticed that all traffic was coming to the invalid because Vultr is not validating itself. Right, so a query would go all the way to from a valid path all the way up to Vultr, and then Vultr would say, yeah, I do have this IP address in my network, but there is a better one, a more specific, in Amsterdam. Let me direct you to there. So yeah, so this is just a story, and I guess I suggest, I have to think about this myself as well. But I guess the more validation there is, the better it is for everyone.
So in the end, I think for sending out responses, you don't care, but you want to be protected yourself. So that's why you need this kind of validation. Because if someone hijacks your authoritative, then yeah, you won't get the responses.
Relying on authoritative name servers to filter out clients who are sitting behind invalid routes is kind of pushing everything backwards.
Right.
It's sort of doing the wrong thing the wrong way. And we can probably expand this at length offline, but you know, I understand the desire to measure things, but not all measurements are equal and not all results are as impactful as others.
Yeah.
That's all. Thank you.
And then you also had the question about if we measure the path, if we see if there's route origin validation happening on the path.
Well, this is getting into your trace route ROV
Yes, yeah,
problem.
of course,
Of
yeah.
actually trying to find the point at which
Yeah.
filters are applied, because downstreams
Yes.
from that tend to use alternate path mechanisms
Yeah.
when there is route blocking going on. And this is why most of the situation becomes context-based, not absolute.
Yeah.
Louis Mycan, and I've been looking at RPKI adoption by the authoritative servers and whether they protect themselves going out. Like, I have the same concern as what Jeff is saying. I won't go through that again. But the two things I'd point out, one, it would be good to see how, in your experiment, how many times the information is dropped because the validation coming back to you is tossing it because you went to a wrong authoritative server, right? That's protecting you more than protecting the servers out there. I think that's an important thing to measure. Because like I say, with Jeff, I had the same idea, like who cares where it came from, I'm going to answer. But the other thing I'd be careful in your percentages is that a lot of times name servers share the same process. Like I might have NS for this name, but they're all the same process. Now they may be a same machine, they're behind a load balancer, and so on. There's so many ways that things are combined down there. What I've concentrated on is I look at the prefix. And everything that's behind a certain prefix, I give that a rating, a so-called rating about RPKI, whatever I'm measuring. So you might want to be careful with saying that all these names are protected. They may have been protected because one hoster is protecting the route to thousands, literally, of machines out there. Be careful of that in your numbers and when you break things down. That's the other advice I'd have.
Yeah. Okay. Thank you.
Thank you, Son and Brice. All right, our next speaker will be Momoka Yamamoto, and he will talk about having your resolver in an IPv6 only network and not being part of the infrastructure that also does IPv4.
Hello. Stop. How do I use? Oh, okay. Hello. I'm Momoka Yamamoto, and I'm from the University of Tokyo. And today I want to talk about IPv6 only recursive resolvers. I wrote recursive resolvers, but I think iterative resolvers is the right term. So whenever I say recursive resolvers, just change it to iterative resolvers. So here's the background, but you can just read it. I'm going to talk about my personal experience. So back in Japan, and me and some other students, well, the other students are doing it mainly, but we are operating an autonomous system that's mainly run by IPv6 networks. So all the BGP stuff, it's all done by IPv6. So we want to do everything by IPv6. So a few months ago, we thought, until a few months ago, our recursive resolver was just forwarding every DNS thing to DNS.Google. So we weren't doing the iterative part. But a few months ago, we thought we should do it by ourselves. So we made an iterative recursive resolver, but it wasn't working because we couldn't resolve some names by only IPv6. And I thought that was a problem, and I think this problem has been here for a long time, but it hasn't been a big issue. But now, because IPv6 is increasing, I think it's also going to be an issue, so I'm here to talk about that. And because I think everyone knows more about DNS than I do, I want to ask how you think about it. So here's the objectives. As I said, we are operating an IPv6 only network, so we want to run everything by only just IPv6. But we still need to be able to connect to IPv4 only hosts. So to do that, we use DNS64 and NAT64. And because we want everything to work with IPv6, we aim to concentrate IPv4 operations on the NAT64. So we only want the NAT64 to have IPv4 addresses, and we want all other applications to only have IPv6 addresses. So that includes the name server. So on the left, we have the example on RFC 6147, DNS64. And in that example, you can see in the red circle that the name server is in between the IPv6 network and the IPv4 network. So it has both an IPv6 address and an IPv4 address. And so that was the example in the RFC for DNS64. But I want to propose an IPv6 only name server, which the iterative name server is inside the IPv6 network, and it only has an IPv6 address. So we want an iterative resolver that only has IPv6 address. So that's what we want. But there's an issue for having an IPv6 iterative resolver, is that we can't resolve some names. So this is an example of me trying to resolve IEEE.org, and I go to the web server. The web server is IPv4, IPv6 dual stack, so it gives me a response, and then I go to a0.org affiliates nsd.info, and that's also dual stack, so it gives me reply, and then from the reply I want to go ask ns1.ieee.org, but because that authoritative name server is IPv4 single stack, I can't reach it for my IPv6 only iterative resolver, and so I get unhappy, and I can't do the name resolving things, and it's a failing resolver. And I did this experiment with the top 500 domain names. 500 is not enough. I should have done more, but bear with me. 500 name servers, and I resolved those 500 names using an iterative resolver that's running with IPv4 and one that's running with IPv6. And when I use an iterative resolver that's running with IPv4, I was able to successfully resolve A records, so 93.2% of the 500 domain names. But when I used an iterative resolver that only had an IPv6 address and could only send IPv6 packets, I could only resolve 98% of those 500 names. So that was quite sad, and these are some of the domain names I couldn't resolve, and you can also try yourself with digging at my name server that's at 2001/200/01CD1:20. So it's a very sad thing that my IPv6 only iterative resolver can't resolve all names. It can only resolve 15% less names, and this is my experiment with 500 domain names. So if I do it for more domain name, I think I will fail a lot more. So, and this is a reference to RFC 3901, Best Current Practice 91, and in Section 4, DNS IPv6 Transport Recommendation Guidelines, it says that every recursive name server should be either IPv4 only or dual stack. And that's correct, because if you only have an IPv6 address, you can't resolve some addresses. So this is correct, but so IPv6 there's more IPv6 networks than it has in the past, and there's more IPv6 networks, and I think there's going to be more IPv6 only autonomous systems like ours, and we need an IPv6 only iterative resolver because we want our own iterative resolver, and we don't want to be asking Google DNS.Google all the time. So how can we achieve IPv6 only recursive name service? I came up with 2 ideas, and I think because you guys are DNS experts, there might be more better ways, but here's the two solutions I've thought of. One is to change all the authoritative name servers so that they can have an IPv6 address, and the other is to change the IPv6 only recursive name service implementation. And obviously, giving all the authoritative name servers an IPv6 address is, well, it's physically hard. Giving IPv6 reachability is hard. So the first one, it's hard. So we just, it's the best solution, but it's not the practical solution. So we go to the, wait, they both said one. Oh, well, the second one. So we go to the second one, and the second one is to change the IPv6 only recursive name service implementation. So it utilizes the NAT64 in the network when sending queries to IPv4 only authoritative name service. So we can deploy this IPv6 only recursive iterative name server to an IPv6 only network. So this is how it can work. It's just adding the CLAC function to the IPv6 only recursive resolver. So the resolver can add the IPv4 to IPv6 translation prefix, which is the well-known prefix is 64FF9B/96 to the address of the IPv4 authoritative name server, and then the IPv6 packet can be sent to the NAT64, and the NAT64 can send the packet to the IPv4 only authoritative name server, and then we'll be happy. So it's just simple. It's just putting the CLAC function into the recursive resolver. So this is what I've said. So my proposal is that the network community should normalize IPv6 only iterative resolvers, and as a stepping stone, we propose IPv6 only iterative resolvers under NAT64. I think this is my time, so any comments or questions, please.
Thank you, Momoka. So I see one question from Mark Andrews in the Mattermost channel. He says, this is really a result of choosing DNS-64 as the IPv4 as a service, rather than choosing IPv4 as a service that works for IPv4 literals. Why are we persisting with DNS-64 when it's clearly broken as a IPv4 as a service?
So I think looking at DNS-64 and looking at it as broken is different from the perspective of me, well, a person who just learned about DNS, and everyone who's been in the DNS field for a long time. I think we have a different perspective. And so for the people who's been doing DNS for a long time, I think DNS-64 is broken because you can't do these problems with DNSSEC, and I think you guys don't like that. But for me, I feel like DNS-64 is just, like, it's great because the application is under the illusion that it's talking to an IPv6 server when it's like just only talking to an IPv4 server, but like the DNS-64 gives an application an illusion. And I think that illusion is like very good because the application is only sending IPv6 packets and it's not sending any IPv4 packets. And I think that's great in a way that the application is using IPv6 and not IPv4. So, well, I don't know if that's answering your question, but.
Thank you. Ralph.
Ralph Weber, thank you for the talk. And I just looked at I gave a talk in 2016 about V6 and V4 resolvers and over a larger data set. So, I mean, that numbers are probably no longer accurate, but it was more like 20% of the names could be resolved with V6 only. So it was really that low. Now, on the recursive resolver, I mean, these things are, or iterative resolver, these things are complicated, and adding another complication with an already kind of weird adaptation mechanism that is in there, which DNS-6.4 is, I mean, as you said, the DNS people don't like it that much, I think adds too much complexity. It's much easier to put just the DNS server on the kind of v4 internet because it serves multiple kind of people in the v6 region.
Yes, that makes sense.
One more question.
Hello, Lars Lima from NetNode. Thank you for a very good presentation. I think I'm slightly in a different camp than Ralph, because I can certainly see that we have a future where IPv6 only networks, and we need to adapt to that sooner rather than later. So I think one thing we could do is to actually update 3901. It's an 18-year-old RFC. The net has evolved since then, and I think we should put efforts into actually updating the recommendations for DNS servers. If anyone thinks different, then I would happily take a discussion in the break. Thank you.
Thank you.
Thank you, Liman, and thank you, Momoka, for this presentation.
Thank you.
Okay. The next speaker on the agenda is Andrew Campling from 419 Consulting. And he is going to present on the impact of Encrypted Client Hello on network operators. And I'd like to remind you that a poll will be posted on the workshops channel in DNS-OARC MetaMost. And it's very important that you participate in this poll, as this is the only way for the program committee to see what you think of all the talks. Thank you. So, Andrew, take it away.
Thank you. Right, good morning, everyone. I appreciate I'm between you and coffee, which for those of us that were out late last night is going to be an important break, so I will roll through this. Just as a reminder, as I'm sure you're all aware, encryption is being used and been focused since 2013 to really encrypt all the remaining unencrypted parts of the internet as a result of Snowden and other activities. And sort of relatively recently, in the overall scheme of things, a lot of the developments have focused on encrypting the DNS and related elements, which are some of the sort of few remaining unencrypted outliers. So I'm just going to refresh your memory on some of the more recent developments and then just pose the question about their effectiveness. So clearly you all know what the DNS is, I would hope, otherwise why are you here? Interestingly, in the IETF, there was some dispute as to whether the DNS is in fact a control mechanism, which I thought was an interesting thing to query, because it certainly is, be that in the consumer space with, say, things like parental controls in many markets, or malware filtering, and certainly in the corporate space with malware filtering, cybersecurity, etc. And obviously a lot of the recent developments with encrypted DNS have, depending on your point of view, focused on improving user privacy of those queries, or in reality, if in my view, have been brought in mainly to make browsers faster. And it's just a happy side effect that they could arguably improve privacy. We've also seen the rise of cloud-based resolvers over the last few years, which certainly gives more user choice, and in some markets helps you to bypass restrictive filtering. On the other hand, when you look at the market share of at least one of those cloud-based resolvers, it's yet another instance of greater consolidation of internet infrastructure, which is a sort of general direction of travel, and arguably long-term effect of that is to reduce the sort of resilience of the internet. And dare I say it, since we're in Europe, if you do choose to use many of the cloud-based resolvers, you are sharing a lot of personal data with US companies. And you're sort of putting that data outside of the protections of GDPR if you follow things like the Schrems II ruling and so on, with a lack of sufficient protections for data. And of course, if you're a network operator, be that a public or indeed a private network operator, if you lose visibility of the DNS data, that's not helping you in terms of things like understanding the traffic flows on your network, so helping you with things like network management and network routing, etc. Now, I'm sure you're all familiar with encrypted DNS, which basically, and I've sort of got a diagram which you may be able to see using DNS-OARC TPS as an example. You're encrypting both the query and the result, so an observer can't see what your queries are, what the results are, can't easily interfere with them. But it is worth just remembering that from a privacy point of view, the resolver operator certainly can see. So from a privacy point of view, arguably the only real privacy benefit is that if, for example, I was running an ad tech business, my competitors can't see the data that I'm gleaning by running a resolver. So it's protecting me as the ad tech operator rather than necessarily a user from a privacy point of view. In terms of how readily users can take advantage of the sort of choice of encrypted DNS resolvers, it's worth remembering when Mozilla sort of first launched support for DOE on Firefox, it put this dialog box up, which obviously encouraged you to, without really reading the text, click the nice friendly blue button, because that's what most users do, because who doesn't want more security? Of course, what it didn't do was actually check whether you were getting any more security, because it didn't bother to look to see whether your existing resolver was encrypted. It didn't understand whether your existing resolver gave you things like malware filtering, because at the time this was introduced, it routed you through to Quad 1 as your resolver, and as you may know, that sort of the main Cloudflare resolver doesn't do malware filtering. It's completely unfiltered. Which, personal view, for any sort of mainstream consumer service, I think that's a really poor choice, not to at least block malware on the resolver. I appreciate that some people need access to that, but not as a mass market service, in my view. More recently, as Chrome and Windows 10 introduced support for encrypted DNS, both adopted the so-called same provider auto-upgrade approach, which essentially means they looked to see what resolver you were currently using, and then had a mapping to see if that resolver operator also provided an encrypted option, and sort of seamlessly moved you across to the encrypted option on the basis that you'd have the same policies, same protections as you would have done with the unencrypted version, but with the advantage of encryption. Downside of that approach was it basically relies on a manually curated list for each of the different companies doing it, and it only works with resolvers that operate with public IP addresses. So it doesn't work for many ISP-operated resolvers which run behind private IP addresses. And that's really what's led to, within the ITF, work on a more standards-based approach for resolver discovery, which is obviously long-term, that's far more beneficial for the industry. The two main activities, DDR, or discovery of designated resolvers, and DNR, discovery of network resolvers. Both are making good progress now. Early deployment already with DDR, which is arguably the more sort of simple of the two protocols. As you can see, Cisco, Microsoft, Quad9, Cloudflare, Apple already got support for DDR. DNR probably is the better long-term option, certainly for, again, if I look at the European market, it's the better option for ISPs, for example, where they run their resolvers, as I mentioned earlier, on private IP addresses, usually with forwarders. So DNR is the better solution to sort of maintain that architecture. The two sort of drafts have cleared sort of the bulk of the standards process. Both have been sort of approved by the IESG, so are not so far off becoming standards. So that's a really positive development. You may have come across Oblivious DOE, which is intended to solve the problem of stopping the resolver operator from being able to track you, which I mentioned earlier, which DOE and others don't solve. And so briefly, that requires two different proxies, one to hide the query from the first proxy, so it just knows where the queries come from but doesn't know what the content of the query is, passes it to a second proxy which doesn't know where it originated from, but then sort of unencrypts the query to get the result and passes it backwards down the chain. Superficially, that gives you very good privacy. I say superficially because you don't know whether the proxies are colluding, and there's no protection for that within the protocol. Apple uses Oblivious within Private Relay, and I'm very confident that's doing it in a responsible way, because it operates the first proxy and third parties do the second. But you could conceivably be running both proxies in the same server. And in fact, some of the performance testing of Oblivious DOE did pretty much recommend that. So you could potentially be operating both proxies in the same physical device, which will give you good performance, but it's be really easy then to pass data between the two, or maybe say, I want to track this particular user, I'll always route their traffic to this dedicated second proxy in order to know all of their queries. So it's by no means foolproof. And in my view, that's in many ways worse than knowing that it's not private, because if you think it is, but it's not foolproof, then that's potentially really unhelpful for users. So the reality is that you don't necessarily have privacy with the various encrypted DNS options, and it's worth remembering that, of course, the SNI data is still plain text anyway. But as you may know, there's work's underway to address the SNI data. Originally, if unimaginatively called encrypted SNI. More recently, it's evolved slightly and is called Encrypted Client Hello, or ECH. When you consider how the SNI data is used, again, it's used, one of the RFCs talks about unanticipated usage of SNI data, and sort of essentially suggests that, well, because they're unanticipated, that we shouldn't care what those uses are, cheerfully disregarding the whole history of permissionless innovation in the internet. So, for example, many schools and businesses use SNI data for content filtering, and in fact, in some markets, so in the UK and the US, schools have to have content filtering. So if you encrypt the SNI data, that becomes a problem because it stops working. Many enterprises use SNI data to implement transparent proxies, and that's how they support bring your own device in enterprises in a very light touch way. On public networks, SNI data is used for zero rating of some content. So if you've got users with data caps, so typically in many markets that will be the sort of cheapest sort of budget options, be it on fixed or mobile networks. They might find that without warning they've used their entire data cap for what should have been zero rated content because ECH makes it impossible to do the zero rating. And it's a very important piece of data for cybersecurity in enterprises. And really where that takes us is the intent behind the encryption of the sort of DNS and SNI data is entirely reasonable, which is to enable a user to communicate with a target device without being observed and without any interference in their communications. But there's some additional consequences of this encryption, which are actually it becomes really difficult to prevent communication with malicious content because you're starting to remove all of the remaining defenses to those protections. It actually leaves you wide open to surveillance by client software and makes it really difficult to spot that surveillance because in essence the client software becomes a black box and you can't tell when it's communicating or with what. In a consumer environment or a school environment, it makes it really easy to access age-inappropriate content and CSAM, etc. Now, again, if I look in some of the sort of standards bodies, often the justification for doing this is to protect dissidents. And the reality is there are far better tools to protect dissidents, so Tor, for example, springs to mind. There are obviously other tools as well. And in fact, some recent research looking in places like Iran, China, etc., Kazakhstan, and so on, has shown that a lot of the blocking that's used actually blocks encrypted DNS and even ESNI. Quite effectively, but that those more sort of tailored tools are continuing to work well. So actually, if that's your concern, there are proven tools which are actually more effective for that purpose. And of course, it's just worth also touching on zero trust. Because again, in the corporate market, you really want to be able to see what's happening on your network, and you have to assume if you can't see it that you have an attacker on your network. And when you lose things like the sort of the DNS and SNI data, as I said, you're losing two extremely important indicators of compromise. And just as a recent example in the US market. We've got in the finance sector 10 finance institutions are about to be fined $200 million each because they can't provide a comprehensive audit trail of all the inbound and outbound communications from their networks, which is a breach of their compliance obligations. Not, to be fair, because of DNS or SNI encryption, but because some of their employees were using WhatsApp and Signal. But I know from discussions with CISOs in the finance sector, that's really woke them up to the danger of encryption, danger in the sense of further fines, further breaches of compliance. So they're starting to track these developments very closely now. Yes, end-to-end encryption can help with privacy, but can have negative operational impacts in certain contexts. And if you weaken cybersecurity defenses, then arguably long-term you're weakening privacy, even though your intent was to improve it. And I think disappointingly what we're not seeing at the moment is some of these developments like ECH being developed with input from the end user communities. And there's not enough understanding of end user requirements within the standards bodies, and that's something I think we need to fix, because the voice of the end user ultimately is really what should be helping us sort of determine how to do these things. And with that, I will stop just about on time, I think, and see if there's any questions. Well, so slightly early. So.
Are there any questions? Also online, you have to post with the hashtag questions pre-pended in the workshops channel. So let me take the time for people to think what they want to ask you a question myself. To do Encrypted Client Hello properly, is DNS-SEC needed?
Sorry,
Is DNS-SEC needed for ECH?
No, you need DO, but not DNS-SEC for ECH.
So are you sure that it's the correct key?
That's a very good point. And I think, to be fair, the same criticism was made of encrypted sort of DNS as well. You're encrypting the path, but you've got no idea whether the content is true. The same criticism still applies. If you really need DNS-SEC to be able to rely on the answers you're getting. Otherwise, you've got an encrypted lie rather than an unencrypted lie, which is not especially helpful. Yeah, good question.
Yeah, I think to add up on that, I think you need a secure DNS protocol to make sure that you don't leak the name in the first place. But you need DNS-SEC to validate that the content you have is the one from the name server.
Right.
Any other questions? If not, then thank you, Andrew, for your talk. Yes, so again, big thanks to all the speakers, Andrew, Momoka, Sandra and Brice. Also, thank you for Runit and SOX for hosting this venue, and also thank you to VeriSign to be the 2022 workshop patron. So, reminder, lightning talks are still accepted, but the submission deadline is the end of session 2, so the start of the lunch, which is 12:30 today, our time. We will now have a bit more than 30 minutes break and start at 11:05 on the spot. Thank you.